So lab 3 discusses a black hole. So in this lab we created an orbit of a star around a black hole, and each person was assigned a unique star trajectory based on their Georgia Tech email. A code was then written in GlowScript to model the trajectory and calculate the net forces acting on the star at different points, and the code was also used to calculate the mass of a black hole. So in this lab, Newton's second law is still applied. However, the aspect of curving motion was added. And in terms of curving motion, there are two different aspects of the net force that are acting on an object. One aspect is the force in the parallel direction, which is F net is equal to d times the magnitude of p times p hat. And another aspect is the force acting in the perpendicular direction, which can be written as F net is equal to d times the magnitude of p times p hat divided by delta t, which is change in time. So then the total net force on an object is the sum of the forces acting in the parallel and the perpendicular directions, as shown here. So when we take a look at our code, we see that the seed is my Georgia Tech email, and this creates the unique trajectory of the star. If we scroll down to where our variables are, our first variable is g, the gravitational constant, which is 6.7 times 10 to the negative 11. And then we were given the star's mass as 2 times 10 to the 30, and delta t is the number of seconds in a day, so that is 86,400. And then we have to define our initial and final momentum. So momentum is generally defined as mass times velocity. So to find initial momentum, we did the star's mass times the initial velocity, and to find final momentum, we did the star's mass times final velocity. Delta V and delta T are the change in velocity and change in momentum respectively, and those are defined as normal as velocity final minus velocity initial and momentum final minus momentum initial. We then calculate dp dt, which is our net force, and that is delta P over delta T. And then again we say here that our net force is equal to this dt, according to Newton's second law, is equal to the dp dt. We then need to split this net force into two different components, the parallel and the perpendicular. So first what we need to define is p hat, which gives us our direction, and that is equal to momentum initial divided by the magnitude of the initial momentum. And then we define d magnitude p dt, which is equal to magnitude of the final velocity, final momentum minus the magnitude of the initial momentum divided by change in time. And then we can say that the dp dt in the parallel direction is equal to this d magnitude p dt times p hat. And then we can say that f net parallel here is equal to this dp dt parallel. Next we can calculate the perpendicular force, where we can say that dp dt perpendicular is equal to dp dt, which is the total net force, minus dp dt in the parallel direction. And then again we just say the force in the perpendicular direction is equal to dp dt perpendicular. Finally, we need to write a code to calculate the mass of the black hole. We define first our position vector r as the origin of the star minus the star's position. And then we can define the mass of the black hole, and we say that it is the magnitude of the net force times the magnitude of the position vector squared, and that all is divided by the gravitational constant times the star's mass. And then we also created arrows shown here to depict the individual forces. So then when we run this code, we can look at the elliptical orbit and see that the magnitude of the forces shown by these arrows here are increasing and decreasing based on the position of the star. We can also see that the mass of the black hole isn't constant throughout, for example, like comparing these two values here, and we'll discuss that further. And then also at the bottom we see here that the F net is printed, F net parallel, and F net perpendicular. So some of the errors, as I mentioned, we see that the mass of the black hole didn't remain constant, and this can be attributed to numerical errors within the trajectory itself. And since we derive the mass from the trajectory data, the numerical errors cause the mass to fluctuate by a small amount. So how exactly does the parallel and perpendicular components of the net force differ from the parallel and perpendicular components of the rate of change of momentum? So when we look at it, they're very similar, as Newton actually intended or actually wrote his second law to be the rate of change of momentum to be equal to the net external force on an object. However, when we look at the two, we see that they're in a codependent relationship, kind of like a cause and effect. So a net force acting on the system is what causes a change in momentum, meaning that if we want a change in momentum, we need a net external force to act on the system. Therefore, net forces cause motion while momentum keeps the object moving. So if the black hole in our simulation was removed and replaced with another one, and the motion of the star remained unchanged, we could not really find a value of the mass of the black hole that was different than the original one, due to the fact that the only data we have is position data, which we know is remaining the same. Since we know that the black hole is the only force acting on the star and the trajectory is unchanged, the mass of the new black hole could not be different from the first one since the trajectory is the exact same.